Hello, my name is Elizabeth Sampley. My partners, Chris, Jeremy, Cameron, and I are going to talk to you today about designing a cruise control system. So, why are cruise control systems important? I, for one, don't use my cruise very often because I like to feel in control when I'm driving. However, for autonomous vehicles, adaptive cruise control ensures the safety and well-being of the passengers. So, uh, we're not going to go into detail about designing an adaptive cruise control system for something like Tesla, but we will cover some basic design features that standard cruise control systems should have. The overall goal is for you to set your cruise at a certain speed, and your car will speed up and reach the desired velocity, and you should feel like you're driving on a straight, smooth track, just like that. What we don't want is for you to set your speed or your cruise control and for you to feel like you're going through a loop. Also, we want for you to set your cruise control and be able to maintain speed when you're going up or down hills. So if you were driving on something like this, we wouldn't want this to happen. It worked that time, but you get the idea. We don't want you to start going up a hill and then slide back down. Your car should maintain speed. So my partner Jeremy will now discuss the different features of our cruise control system that we would like to include.
Hi, I'm Jeremy Ingles, and I'm here to talk to you about the criteria to consider when designing a control system. Three criteria we need to consider are stability, transient response, and steady state behavior. Stability is, does your system reach your desired behavior? Transient response, we need to consider rise time, settling time, and overshoot. Rise time is how quickly does your system get to your desired velocity. Settling time is how long does it take your system to settle on that velocity. And overshoot is how much oscillation do we have on that velocity before we reach our desired velocity. Steady state behavior, we need to consider our air, how close to our desired behavior we want, and disturbance rejection, how well can our system combat any outside forces. When we chose our system, we wanted to look at settling time, overshoot, and disturbance rejection. Our desired output would be a graph like this, nice, smooth, and then we hit our final velocity, no overshoot. What we don't want is a graph like this or a response like this, where we overshoot and come down, oscillate. It takes a long time for us to settle. So these are the main criteria we want to consider in our system. Lastly was disturbance rejection. For our system, we had to consider going up hills and down hills, so we wanted to pick a controller that's going to combat those outside influences. To talk more about our controller selection is Chris Cunningham.
Hello, my name is Chris, and I'm here to discuss controller selection. Often it's helpful to represent your physical system with a mathematical model. And in controls theory, this is known as a block diagram shown on the board. The block diagram takes your cruise control setting, runs it through the mathematical model in order to get your desired output velocity. And even before selecting the controller within our mathematical model, we had already determined that the system was stable. Further selection of the controller allowed us to minimize our design criteria of settling time, overshoot, and disturbance rejection. Through multiple iterations, we determined that a proportional derivative controller would be ideal for this situation. Up next will be Cameron to discuss further controller optimization.
Hello, my name is Cameron, and I'm here to discuss controller optimization. As Chris mentioned, a proportional derivative controller would be needed to enhance our system. The system without the controller could take up to 10 minutes to settle at the desired speed. And while we're more concerned with how long the system takes to stabilize, the rise time to that speed is directly related to our controller selection specifically. So by iterating mathematical values to the system via the controller, we can speed up how fast our system achieves the desired outputs. So if you think about it, we've got our little car, got our hill right here. based on how our system is designed, it will naturally minimize disturbances. For instance, if you're driving on a flat road, which got a little flat road right here, and encounter a hill, the system should maintain velocity within a mile an hour, mile and a half of the desired speed. So if you start going down your hill, you're not going to just go flying and go right off the table, right? You're going to go down that hill and maintain your speed relatively close to exactly where you want it.
Moving on, the best way to understand how the system responds to different proportional derivative controller inputs comes in graph form, and the interpretation of those graphs tells us how our system responds. To the left, we have a Bode plot, so that's this guy over here. The top graph shows the magnitude, and the bottom graph shows the phase of a velocity input. The first thing to look at is the phase graph down here. Notice that it never crosses negative 180. It's right about negative 190 right there. This tells us that regardless of how we adjust the values associated with our controller, it will never become unstable. Let's look back up here at the magnitude plot and notice that it crosses 0, so 0 is right down here, at about 1. This crossover frequency, which we draw a line, this is the crossover frequency, which we draw a line straight down here, we're about negative 90 degrees. Now, what we're looking at is how far away that is from negative 180. In this case, it's negative or 90 degrees. This is our phase margin. That tells us that we have about 90 degrees of frequency shift. That means that we can have a time delay of about 1.6 seconds before the system becomes unstable. Now, if we look over here at the Nyquist, notice that it does not encircle negative 1. Negative 1's over here. This thing exists entirely in the right half plane. This tells us that our system is stable.
In closing, we would like to summarize the results of our cruise control system design. From the beginning, our system was stable and it had 0 overshoot. However, it suffered from a long settling time and it failed to reject disturbances. The addition of the proportional derivative controller allowed us to reduce the settling time to less than 4 seconds and also reduce the effects of disturbances. For example, we tested our system using a 5-degree slope and verified that the change in velocity was only about 1.5 miles per hour. This is acceptable for everyday driving. However, future design iterations might include a PID controller instead. This type of controller would totally negate the effects of disturbances such as a change in slope. Additionally, this type of controller would reduce the steady state error, the error between the velocity output of your car and the velocity setting on your cruise control to 0. Finally, we would like to encourage listeners to check out MATLAB's SIZO tool and Simulink functions when designing your own control systems. Thank you for listening.